the next is spring potential energy, right? So this is the work done to stretch or compress a spring by a certain displacement from its relaxed position. From its relaxed position. Okay. All right. So how do we do it? Well, let's think about what's happening first. Let's think about compression first. Right. So we put a box over here. All right. So this is the relaxed position, and if you compress it, okay. So we are gonna be working in just one dimension. So I'm gonna use the standard. Right. This is x, and I'm gonna make x equals 0 over here. X equals to x final over here, and this is going to be, so this is x equals 0. This is going to be negative delta x. Okay, so delta x is the amount of compression. So this is delta x, right? So if I've compressed it by 1 centimeter, if this is x equals 0, this better be minus 1 centimeters, right? Like that. So if I compress it by 1 centimeter, if I stretch, it's going to be the same thing. You'll see it's a square later on, so it doesn't matter too much. All right, during this process, right, what is the force? If you compress it, the force, let's say you're halfway through, throughout this moment, as soon as you start compressing it, you'll experience a restoring force trying to push it back. So the spring restoring force is pushing this way. And we've talked about, right, it's minus k delta x. So you see my delta x is, as delta x is negative, it's pushing towards the positive way. So at any point, it's actually, so yeah, delta x, but so that's x minus x equilibrium or x relaxed, and x equilibrium is 0. So it's just minus kx. Okay, so this is the force of the spring. Okay, so what is the work done of the spring when you move it from here to compress it? Okay, so there's a couple of ways to do this. We can use the simple definition or the second level one or the third level one, right? In terms of complexity. Let's start with the simplest one, all right? So what is the displacement? The displacement is this way, right? That's the displacement vector. It went from here to here, right? So the displacement is this way, but the force at every point in your displacement is pushing that way. So they're anti-parallel. Right, so the work done, I need to use minus of the magnitude of the force times the magnitude of the displacement, right? Magnitude, just to emphasize that magnitude. Okay, so what's the force? Well, minus kx. So the magnitude is kx. Okay, and what's the magnitude of this? Well, let's see, so you see some issue over here if I use this, is because I'm using it as if the force is constant. So I cannot use this formula because what I will get, in fact, yeah, if you just naively put this in, right, you'll see you come out with a problem. You get this, which is not what we want. What was the issue is because I assumed the force is constant. However, as I push it over here, it's just a small compression, and you see that x is still, the magnitude of x is a small value. The force is very weak. The more I compress it, as much as this changes more and more, the force actually increases. So the force actually changes along the way. What does that mean? Unfortunately, we need to use the most complicated one because force changes along the way, right? So we need to use this. Okay. Now let's put in all the vector form, right? So we cannot get away from that, but you'll see it's actually not too difficult. So it's minus kx in the x direction. Is it going in the y direction? No, the spring is not going. Okay, so that's the force. And dr, again, sorry, delta r, again, it's dx dy, just like that. Okay, so now you can put this in. Let's see if we get the signs correct as well. Minus kx 0 dot dx dy. Okay, so this is the force of the spring because it's work done by the spring. Okay, and by the spring's force. Okay, so we see this K is a constant. I can pull out the minus K. Should I? Yeah, let's do the dot product first. All right. For the dot product, this times this, so I have minus K x dx plus 0 times dy, which is just 0. And then now this K is minus K is constant. I can pull that out. Initial final x dx. And here I have from initial to final, right? So integrating this 1/2 x I f like this. And then I can plug it in K, right? 1/2 x final 1/2 x squared. So x final square minus 1/2 xi squared. Okay. So if you gather this up, you can see I can pull out the 1/2. So I have minus 1/2 k and delta x squared over here. And you see this is right. So you see there is a minus sign. So if my my initial, where was it? Initial is 0. Okay, so I can actually plug that in there just to get it a little bit nicer. So I have initial is 0, so I have minus 1/2 k x final squared, and that's the compression. Okay, that's how much it has compressed. Now you see this minus sign. Why is that? Exactly because of what we talked about, right? So which way is the force pushing? The force is pushing this way, but you are moving it this way. So what's the work done by the spring? They are working anti-parallel towards each other. So that's why you have a minus sign over here. It's saying the work done by the spring to compress it. The spring is not doing anything to compress it. You are doing something to compress it in some sense. So so that minus sign is telling you that essentially the spring is rejecting your compression. Okay, and you can do the same thing with pulling it. But either way, this is sort of the amount you have compressed. Either way, you'll see you will get a minus sign by the work done by the spring. Okay, so if the work done by the spring is negative, so how much energy is stored over there? Okay, so then the amount of energy that is stored will be let's think about in terms of the magnitude, right? If I need to provide, so how much energy I need to provide to squeeze it? Okay, so the spring just lost in some sense, right? Work done is the energy required to achieve this process. So the spring just lost 1/2 k x final square amount of energy, right? So by pushing it over here, the spring lost that much energy. So where does that go? The energy cannot, you've calculated this, so it's this amount of joules, right? It's negative. This is a positive number, this is a positive number, but there's a negative in front, so it's a negative. So the spring lost that amount of energy. Where did it go? It must go into the amount of energy that is stored in here that later on it's going to use, right? So the spring lost that much energy, so it must mean, in other words, you have to provide that energy. You have to provide that energy to push it in. So it must have to store that amount of energy that later on it can use to sort of push it back out. So the stored energy by the spring must be the same amount. Must be the same amount. Okay. So the potential energy is so the amount of work to push it back to the initial position. So if we look at the definition carefully, I think it makes sense to yeah, maybe I should say work done on the object by the spring to push it to the relaxed position, then it will be sort of negative of this. Either way, you can think of that is the amount that is stored, and later on, it is transformed into kinetic energy. In a practical situation. In practical situation, it's usually unambiguous which way you need to use it. Okay, so just to illustrate that fact, but at least you see where if the sign is confusing to you, don't worry about that too much. You can at least see sort of where the half kx squared comes from, just having minus kx over here. Okay, so in practice, you can see, for example, if I have something that is compressed, okay, so what is the kinetic energy over here? Let's say it's 0, I release it at rest. And what's the spring potential energy here? It's 1/2 k, let's say this is x, right? X squared, so that's you can write delta x or x either way. And when it goes all the way back to here, what's the spring potential energy? So it's no longer, so now it's at a relaxed position. So it's no longer compressed. So there's no more stored energy in it. So what is the kinetic energy? So it must be, this amount must go all over here, right? And you can find, well, it's half mv squared, and you can now find out what the speed is. Okay, so you can do a simple this plus this equals this plus this. So you'll see 1/2 kx squared equals 1/2 mv squared. So this is you can look through one of the examples in the book, for example, in example 7.5. You can check that out. And you can calculate what the final speed is. The final speed when it arrives here, so the half cancels out. And you have kx squared over m. And you can take the square root, plus or minus. But if you care about the speed, it's always plus. Okay, so you can see it's immediately very easy to calculate what the speed is over here. Can you do that with Suvat? Can you do that with kinematics equations? No, because the force is constantly changing at every point. So if it's constantly changing at every point, the acceleration is changing, right? Equals to ma, right? So the acceleration is minus kx over m. And at every point, it's different acceleration. So you cannot use the Suvat equations, which is only applied to constant. But with energy approach, within basically two lines, essentially 2 or 3 lines, sort of some mental algebra there, you can immediately calculate the final speed it is relaxed into.